these famous scientists are giving incorrect accounts of the Michelson-Morley experiment. In fact, the Michelson-Morley experiment didn't really show anything.
Have we been misled about how groundbreaking scientific discoveries actually occur? Professor Harry Collins, a pioneering sociologist of science, argues that our current understanding of scientific discovery is shrouded in mythology. In this eye-opening episode, we peel back the curtain on this messy human process of scientific advancement, from the misrepresented Michelson-Morley experiment to the behind-the-scenes drama of detecting gravitational waves. Professor Collins' fractal model of society reveals a controversial reality. Our beliefs, our skills, and even our sense of truth are determined by the social groups we inhabit. We explore Collins' radical vision for reimagining scientific education, dismantling competitive structures in research, and positioning science as a vital check against the erosion of truth in public discourse. Welcome to the Theories of Everything podcast. This is for the Rethinking the Foundations of the Academy series. How can we improve scientific inquiry? Please take it away.
Okay, well, I'm going to talk to the question I was set, which is how to improve science. But I've got a funny version of how you improve science, because I think of science rather differently to most people. And the big contrast here in what I'm going to say is between science as a cultural institution, which is what I'm interested in. The thing that science does as a cultural institution is discover truth about the observable world, and I believe influence society. And in my view, it should influence society a lot more. On the other hand, there's often a tension between that, science as a cultural institution, and science as a profession. Science as a profession creates people's careers, creates wealth, and creates power. And sometimes science as a profession gets in the way of science as a cultural institution. Now, how could science be improved? Well, it depends what you think science is for. One of the things that science does is discover true and useful things like vaccines, the importance and consequences of the increasing emission of greenhouse gases, the causes and consequences of the whole of the ozone layer, and things that lead to economic and military power. And another thing science does is to discover true, but not so much useful, but edifying things like the fact that there's been a big bang at the beginning of time, the fact that there are black holes, which are very odd things indeed, the fact that there are gravitational waves, which I've put in a square box because it's something I know a lot about. I spent about 45 years studying or hanging about with the scientists who discovered gravitational waves. Yeah.
Great.
But the thing that I'm really interested in is science's role as a foundation for democracy, because I think we've got to have it to stop the erosion of truth. And to stop the erosion of truth, science can be a check and balance for pluralist democracies in the way that the rule of law is a check and balance, if it works, if the rule of law is working and hasn't been eroded. And science, even more importantly, can be an object lesson for the importance of truth when you're trying to find things out, to work things out, to work out how to run things, and so forth. And in that sense, it should be at the heart of democratic culture. Right now, I believe this, and this is why I'm doing this kind of work these days. Right now, Western democracy is in greater danger than it has been since the 1930s. So I'm going to make the outrageous remark that saving democracy is probably science's most important purpose. But using science to save democracy does involve some improvements to science along the way, such as, well, citizens and professionals, note that I say citizens and professionals, must come to understand how science works and why it is the best institution for uncovering knowledge about the observable world. Currently, how science works is mostly shrouded in mythology, and that's true for the professionals too. And we must recognize certain professional activities masquerading of science that aren't really science at all. Much of economics is like this. Maybe string theory is like this as well, as Lee Smolin would suggest, and various other people would suggest. And the other thing that I think needs to be done, though, how on earth we're going to do it, I don't know. is to make the profession of science less competitive and stop people turning it into a marketable commodity. It's got more important roles than that.
A marketable commodity?
Yeah, I mean, well, somebody who's been working in a university for years and years and years among scientists, there's a tremendous temptation for scientists to sell science as something that's good for the economy and to allow science to be judged by how much it contributes to the economy and to judge our activities as university professors by how many papers we turn out, what sort of impact we have on the world and things like that. Whereas actually there needs to be more emphasis on uncovering the truth as the purpose of science. And that tends to be in tension with all these marketable versions of science.
All right.
Now, let me just illustrate one of the problems that science has. I said the way science works is embroiled in mythology. Here's an example. Here are two book covers. One called The Evolution of Physics, which was written in 1938 by Albert Einstein and Leopold Infeld, and the well-known book A Brief History of Time, which is supposed to be popular, though heaven knows how many people can actually make head or tail of it. I can't. But it's written by Stephen Hawking, who is probably one of today's most prestigious scientists. Now, let's see what Einstein and Hawking have to say about a famous experiment, the Michelson-Morley experiment, which was conducted in 1887. So in 1938, Einstein and Infeld said of this, in view of the small time differences following from the theory, very ingenious experimental arrangements have to be thought out. The Michelson-Morley experiment was supposed to be measuring the speed of the Earth through, as it circled the sun, and it was supposed to be measuring this by looking for changes in the apparent speed of light as it was measured on the surface of the Earth. So in view of the small time differences following from the theory, very ingenious experimental arrangements had to be thought out. This was done in the famous Michelson-Morley experiment. The result was a verdict of death to the theory of a calm ether sea through which all matter moves. No dependence of the speed of light upon direction of travel of the Earth could be found. Every experiment has given the same negative result as the Michelson-Morley one and never revealed any dependence upon the direction of motion of the Earth. And in 1988, probably echoing this and many, many physics textbooks, which also say the same thing, we've checked them out. In 1887, Albert Michelson and Edward Morley carried out a very careful experiment at the Case School for Applied Science in Cleveland. They compared the speed of light and the direction of the Earth's motion with that at right angles to the Earth's motion. To their surprise, they found they were exactly the same. Well, historians going back to the Michelson-Morley experiment have found that none of this is true. This is both of these famous scientists are giving incorrect accounts of the Michelson-Morley experiment. In fact, the Michelson-Morley experiment didn't really show anything. Michelson and Morley wanted to measure the speed of the Earth around the sun through the ether. They set up their very, very difficult experiment. They found nothing and they gave up. To prove that the speed of light is a constant, which is what Einstein would say some 20 years later, required you to repeat this experiment at various times of the year. It was never done. Michelson and Morley just thought they'd done a failed experiment. And by about 1930, lots more repetitions of this experiment were done, and people concluded, yes, there was a difference between the speed of light in the direction of the Earth and the speed of light across the direction of the Earth. Not as much as you'd expect, but nevertheless around a tenth of what was expected. And a man called Miller won a prize from the American Physical Association for finding this and definitively proving that the speed of light was not a constant. Now, the speed of light is a constant, but I think general agreement among physicists who understand this business would be that, in fact, no Michelson-Morley type experiment that could really show the constancy of the speed of light was done until the second half of the 20th century. But nevertheless, as you see, popular books, you can find the same thing in most of the physics textbooks that you take off the library shelf. tell you this was proved in 1887, that it was an anomaly which wasn't resolved until Einstein came up with the theory of relativity early in the 20th century. But it's just not true.
So to be clear, both Hawking and Einstein had the same but incorrect interpretation of the
Yes.
Michelson-Morley experiment?
They tell a mythological version of it, which would say it was done in 1887, and they showed that the speed of light was a constant. It is not true. I didn't do that at all. And what I call is this is the tendency of scientists to want to pull rabbits out of hats. They want to present an image of scientific experiment where you do the experiment, and then there's a kind of logic of science that forces you to accept the result of the experiment, and you find something out almost instantly. Now, I'm going to give you an example of a modern version of this, and it's from the field of physics that I know quite a lot about, and that's gravitational wave detection. This is a set of the front pages of newspapers that were published in February 2016, when everybody was celebrating the first agreed, accepted discovery or detection of a gravitational wave, something which I had followed in great detail. I was in London at a meeting of physicists to hear the announcement, which was actually made in Washington. And then, much to all our enormous joy, the first item on the 6 o'clock news that night on the BBC was the discovery of gravitational waves. And I remember going up to one of my physicist friends at the time and giving him a high five for this wonderful outcome. I mean, it's a fabulous experiment, and it's a great part of my life. Einstein suggested the existence of gravitational waves about 100 years ago, and the experiments started about 50 years ago. And the history of the experiments is very, very checkered. In about the 1970s to 1990s, say, during that 20 years, the detection of gravitational waves was announced about 6 times by different groups. But all of those claims were dismissed by the scientific community. And it wasn't until 2015 that the first detection, which wasn't dismissed by the scientific community, was made. September the 14th, 2015. I remember it very well. I was sitting in this room watching my emails when news came across that some kind of disturbance on the 2 gigantic detectors in America, one in Louisiana and one in Washington State, had seen some signal which looked kind of promising. I knew that more or less as soon as anybody else did in the gravitational wave community. Then, within a couple of days, the physicists had decided, hey, maybe this really is something. I mean, mostly you get this kind of signal, and it's just noise that is dismissed and so on and so forth. But this one looked good. And then I followed in great detail the next 5 months of work, intense work, which was spent trying to work out whether this really was a gravitational wave. Nobody could quite believe it. Had we finally seen a gravitational wave after 50 years? I didn't believe it. I mean, 45 years, and I'd actually finally, was I still around when this momentous discovery was made?
And sir, when you say you followed it, do you mean to say you followed it from the outside as with the information that's accessible to the public, or did you go inside?
I'm inside. Okay. I have all the passwords and everything else to be able to read all the emails which are passing through the whole community. And since this community is scattered all over the world, they were doing the research and communicating about it by email. So I was right in there just as much as any one of the scientists. I was essentially a member of the subject.
It's akin to having security clearance?
Yes, exactly. Exactly. As far as I know, I was the only person who wasn't actually a member of the gravitational wave community who had all these passwords and was able to look at them. Hundreds of emails were coming into my computer every day, and I was reading them all and analysing them all and so forth. Of course, I wasn't making many suggestions. I was keeping quiet, But everybody knew I was there, and everybody knew I was part of it, and so on. And one of the interesting features of this discovery process was that the whole community never met in one place. It was all done via discussion across email with occasional telecoms, which I also was on. I was invited and listened into the telecoms that were going on. But of course, this community had been together for 20 years, so they all knew each other enormously well. I don't want to give the impression that science can be done by telecom and email. It cannot. It has to involve trust, and trust in small groups. I mean, this was a big group for a small group, if I can put it that way. It was about 1,000 strong and scattered all over the world. But everybody knew each other as though they were members of a small tribe. So there was total trust among the scientists. Anyway, after the better part of 5 months, I decided, yes, we're finally sure this really is a gravity wave. It's not anybody hacking into the machines, and it's not noise, and so on and so forth. We're going to announce it. And it was announced in February 2016 to enormous acclaim, including these headlines. And I was writing a book at the same time as all this was going on. Whoops, and that's what the book looks like. It's called Gravity's Kiss, The Detection of Gravitational Waves. And it's one of the chapters in that book that I want to talk about to illustrate this rabbit out of the hat business. Because during this 5 months, we were told we must not let it be known to the public that the community is checking out a gravitational wave. We had to pretend that no such thing was going on and that life was normal. And this was very, very difficult. And people, journalists and other scientists, got the sense that there was something strange going on in the gravitational wave community. It's the same sort of thing as spies discover when they're looking to find out whether the enemy is going to attack or where they're going to gather their forces. You look, you see vehicles going to this place and another place where they wouldn't normally do, and so forth. There were trails.
So it wasn't as if there was a leak. It was that there was indirect evidence.
We don't know if there was whether anybody actually leaked among the whole community. But as far as we know, nobody did. But people managed to work it out. But I can tell you, by the end of the 5 months, certain people had a very good idea of what was going on. And it's almost as though they knew exactly what was going to happen when the announcement was made. But in the meantime, journalists telephoned me and said, I've heard this rumor. Can you tell me more about it? And I'd have to say, well, no, I haven't heard that rumor. In fact, that's true. I hadn't heard the particular rumor that somebody told me. But of course, I knew what was going on, and I knew what he was really asking. But I had to dissemble and fib. I had to tell my wife, and all the scientists agreed that they had to tell their partners, because their partners would see that something weird was happening. I was spending all day and every day on my computer, and the physicists who were working away at their calculations. But I didn't tell my son. And at one point, my son, who knew I was working on gravitational waves, heard the rumor that gravitational waves had been discovered, and he asked me. And I said, look, no, there's nothing to say, Joe. Can't tell you. And that sort of thing is a strain.
Yeah, this is quite odd for people who are listening. This sounds like the Manhattan Project. This isn't an experiment to develop some weapon. This is a scientific experiment, like the Michelson-Morley experiment was a scientific experiment. So people are likely finding this quite odd. And this is cataloged in your book, Gravity's Kiss.
The thing is, it's not odd for scientific discovery. It's the normal way to proceed if you've got a big scientific discovery, because what you want to do is announce it with a big fanfare, which is what happened. And it is, as I put it earlier, it's pulling a rabbit out of a hat. They wanted to pull the rabbit out of the hat. Now, I knew all these people, and I kept saying to them, why are we doing this? Why don't we just tell people what's going on? And people didn't seem to understand what I was saying. They would say, what, you don't want us to do all this checking work before we announce it? I said, no. Just say that we're checking. We haven't found it yet, but we're checking. And they couldn't get it. And I kept asking people, why not? Why can't you do it this way? And the nearest thing that I heard to a reason for not doing it the way I suggested was in case other people started doing calculations based on a guess on about what we were going to see and sort of preempt what we were going to announce in some way just by guessing what it was. So in the book, I write all this up and I present what I suggested should be going on. I mean, I say, call it the 6 stages of unveiling this discovery, though it's purely arbitrary. I mean, you might decide to have 10 stages or 20 stages or something.
When you reference that there's a rabbit being pulled out of a hat, you're referring not to the magical aspect, but to the spectacle of having some inaugural announcement?
The result of a scientific experiment is suddenly to expose this thing. And in the meantime, you mustn't let anybody know that anything's been going on, because that would, as it were, suggest that this would work rather than the equivalent of some sort of logical process.
Ah, okay, that's interesting.
So I said, why don't we do it this way? The first pronouncement should be something like, there's enough going on to make us busier than usual. And if it didn't work out, as it might not, with all this checking, and then you'd say, but it was a false alarm. The second stage might be, we're analyzing data that might or might not lead in an interesting direction. And then we'd have to say, if it didn't work out, well, it didn't lead anywhere. The third stage might be, we're clearing diaries in case we need to make an announcement. If it didn't work out, you'd say, sorry, unfortunately, we discovered a mistake. And then the fourth one might be, a paper has been submitted and is being refereed. So that wasn't accepted. The paper is being revised or has been rejected. And finally, we'll be making an announcement on a certain date unless things go wrong. And if it doesn't work out, further scrutiny shows the result is not reliable. And so you could tell people that you were doing this over this 5 months. You could explain to people the 5 months of work that was going on. You could explain to people that half a dozen announcement for the discovery of gravitational waves had already been made, but didn't work out. And, you could say, we cannot announce this until we've checked it to death. But that doesn't mean to say that you can't tell people what's going on. And my claim is, it would be much better if you did tell people what was going on step by step, because then they would get more sense of the immense difficulty of making a scientific discovery. In this case, this discovery was 100 years from Einstein suggesting the existence of gravitational waves to the final announcement. It was 50 years from people starting to do experiments of it. It was 6 or so failed claims. And then it was 5 months of work from a really big signal to actually being ready to announce it. And then people would get some sense of what science really is, rather than have this mythology that science is a logical process. It's not. It's really hard work. And the work is full of doubts and full of philosophical assumptions and guesses. And this just got to the point where people said, okay, we've reached a point when if we're not going to announce this, nobody's ever going to make a scientific discovery, but people were still in doubt. And one of the things that reassured everybody before it was announced was that a second one was discovered in the course of the checking process. And everybody kind of breathed a sigh of relief. It's not going to be the famous monopole, of which one version was discovered and it's never been repeated. So it was probably false, but at the time it wasn't thought it was false. So that's how science is. It's hard, long work.
Yeah, you also mentioned that there are philosophical assumptions that go into the discoveries in science or the experiments.
Well,
I don't know what you mean.
In logic, you can always doubt something. In this case, the case of this signal, I'll give you an example. One possibility was that malicious hackers had hacked into the experimental apparatus and put false signals in. And so this had to be checked out. And a big analysis was done of how you could get false signals in. And the conclusion was, yes, you could get false signals in. But as it happens, the 2 detectors, which had to report coincident signals for this to count, were slightly different. And in order to put a credible signal in, you'd have to know that difference. And therefore, the hacking would have had to have been done by insiders. And the community said, there aren't enough dishonest insiders to have done this job. That's a philosophical assumption. I'll give you another example. When this discovery was being discussed in CERN by Barry Barish, who was the director of the project at the time, somebody asked from the audience, but doesn't all these calculations and so forth rest on the assumption that the speed of gravitational waves is equal to the speed of light? But that's never been directly shown. I think it was Carlo Rovelli put up his hand, he was also in the audience, and said, look, yeah, that's true, but if we start asking questions like that, we're going to undiscover the Higgs boson. In other words, science works with a trusting community agreeing not to doubt beyond a certain level. Because if you doubt beyond a certain level, you'll never discover anything, and you'll wind up on the scientific fringe rather than the core of science. One of my chapters in another book covers 25 philosophical assumptions that you have to make to discover gravitational waves.
Okay, what's that book called so that people can look it up, and I'll put an image of it on the screen?
Gravity's Ghost and Big Dog. This refers to two false signals that were deliberately put in by the management of LIGO to test their detection abilities.
Understood.
So we're still stuck with rabbits out of hats, and that's one of the things I think we should stop, taking rabbits out of hats in science. We should start introducing people to the fascinating process of the scientific discovery, which is long, hard, open to disappointment. Now I'm going to move in a slightly different direction now. I'm going to try, because as I said at the beginning, what I'm interested in is the use of science as a support for democracy. That's science as a social institution. So now I'm going to turn to look at something which is a bit more my business as a sociologist, not so much, but try and explain where science fits into society, and why I want to see where it fits changed. So let me start off with something which I call the fractal model of society. What is a society? Okay, well, the idea of a fractal enables you to describe a society. All these ovals you see on this diagram are groups in society, but they start at the top and they cascade down to the bottom, getting smaller and smaller and smaller. The top one is the sort of, it's the social group which comprises, shall we say, something the size of a country. And it's characterized by sets of skills, the ability to speak the natural language of the country, the moral sense of the country, and a skill that you learn when you're very, very young, knowing how to tell the truth. And then as you go down, the next level down is also societal wide, but it's more of the little things that you understand as a member of a society. You have versions of what's clean and what's dirty. You understand where in this society, how close you should walk to somebody approaching you on a sidewalk. Can you walk very close and brush against them, or should you stand a bit further away? That depends on the number of people on the sidewalk, how crowded everybody is and what's going on and so forth. People in societies understand these things. If you violate norms, things will go wrong. And, in Western societies like ours, you'll understand a certain amount, you'll have a common understanding of a certain amount of politics. And then we go down and we get smaller groups that are members of this society. Parents are a group. You're different if you're a parent or if you're a non-parent. And there are certain things you pick up as you become a parent and mixing with other parents. Car drivers are a certain very large group in most societies. Office workers are a large group in most societies. Then you go down, on the left-hand side there, I've got shoelace wearers. I put them in because they're not a group. They're a set. There's nothing social that keeps all social. The thing social, you have to learn to be a shoelace wearer.
Okay.
Whereas all the other ones I've learned, you have to learn something social. Scientists, of course, are another group, but they all act in roughly similar ways. One hopes, but a lot of them don't. We'll come to. Christians are a group. Bird spotters are a group. Footballers are a group. Farmers, car mechanics. And now look, as we go down, you see three of the small groups which cascade down from scientists. Physicists, cascading down from them, gravitational wave physicists. And then there's molecular biologists who cascade down from biologists, which are further up. And along the bottom, I've got bricklayers, neo-Nazis, and plumbers. Now, I call this the fractal model. A fractal is very useful for thinking about this because in a couple of ways. First of all, there's something genuinely in common with the fractal and the structure of society. And that is that the small groups that you see at the bottom are also members of the big groups that you see at the top. In fact, they constitute the big groups that you see at the top. And the big groups that you see at the top form the ideas and thinking of the members of the small groups at the bottom. You know, one popular analogy for the mathematical version of a fractal is a cauliflower. And in a cauliflower, you have the cauliflower as a whole, and then the cauliflower can be pulled into florets, and then it has sub-florets within it, and so on and so forth.
Mm-hmm.
And of course, the cauliflower is all the florets, but at the same time, you can pick out any one floret and eat it. So it's a bit like this, the fractal model of a society. And the other feature that fractal-like is that all these groups are the same, apart from the shoelace wearers, which I've got there, and other sets of people. They're the same in that to become members of these groups, you have to learn how to become socialized into the way the members of these groups behave. And then there are features of this fractal-like thing which don't exactly correspond to the mathematical fractal. One thing is you can be a member of a number of these groups, and that doesn't quite match with the fractal. And also the embedding here is very multidimensional, whereas in a cauliflower or a mathematical fractal, it's one dimension. So, you know, it's an analogy, but a useful analogy with some literal similarities.
I see. The one-dimensional aspect of the cauliflower is just set inclusion, you mean?
Well, it's probably, I shouldn't have said one-dimensional because a cauliflower is a three-dimensional thing. But what I mean is there's only one dimension of embedding, one cascade in the cauliflower. Whereas here,
yes,
there's all kinds of strange embeddings. I originally drew this diagram to represent gravitational wave physics when I was trying to understand what sort of society I was investigating. So this is supposed to be gravitational wave physicists and their division of labor. And here you see N gravitational wave physicists all doing their specialism. So there, one of them is calculating gravitational waveform patterns. One of them is designing interferometer suspension design. One of them is a laser expert, and so on. Notice that what binds them together, what makes the division of labor work, is the common language. They can't do each other's jobs, but they can coordinate each other's work because they all speak the common language of gravitational wave physics. It's what I call having interactional expertise, at the top of the label of this slide. And one of the things that's emerged from my study is the extraordinary importance of language. A lot of philosophers nowadays tend to want to elevate the importance of practice, but language is overlooked. Language is absolutely vital. Otherwise, you can't have division of labor because people can't do each other's practices, but they can speak the language. And at the bottom there is that smiling figure with no hammer and anvil.
And that's you.
And that's me. Exactly. That's me because I learned to speak the language, but I can't make physical contributions in the way that the others do. It's not quite true. I mean, I spent enough time talking gravitational wave physics to have made a couple of minor contributions, actually. But that's not my job, so I'm not talking about that.
Sure.
Yeah.
Understood.
So that's me, but it's also somebody like Gary Sanders, who was the project manager of the LIGO apparatus, who agreed with me, and we wrote a paper together about the notion of interactional expertise because he doesn't do the actual practice. He manages it, and he coordinates this work and makes decisions about where they're going to go next. So this idea of interactional expertise is very important, I believe. And I can send anybody the paper, or you can send anybody the paper who wants it, the paper written by me and Gary Sanders.
Sure. The link will be in the description. And also, I'll show a brief image of it on screen right now.
Okay. Well, the other thing to understand about this little diagram we have here is that these people in this group are very, very careful to patrol their boundaries. They don't let anybody in, just anybody in. They don't let anybody in unless they want them in, unless they can make a contribution. That's why I said, was the only person, as far as I know, who had all these passwords and who took an active part in the discussions of gravity waves over umpteen years, decades. I didn't get it. It wasn't easy for me to get in. I had to work harder.
Mm-hmm.
But well, that's part of the job of the sociologist.
Just a point here. Does this characterize data collection or also theorizing? So, for instance, is there another universe, a multiverse, where Professor Harry Collins is doing a talk on the string theory community? I don't imagine that what the string theory community does is under some
No.
password akin to this where you need clearance. But I do imagine that for Bicep, for instance, with Brian Keating's project, that there was.
Yeah. What do you think is the crucial difference between string theory and Bicep? The fact that one of them is theory.
Experimentalists are involved.
Yeah, I don't think that's it. I think that let's not mix up secrecy with guarding your boundaries. Okay, remember, I'm arguing that these people should be opening their boundaries so everybody can see what's going on. But that's not the same as taking anybody in to help them with the project. Yeah?
Understood.
So me, though I was right in there, I knew I had to keep my mouth shut and not start telling people how to do their job. Otherwise, I'd get thrown out again.
Okay, so it's akin to an open kitchen. At a restaurant, not everyone's allowed in the kitchen to cook. The chefs are there, but you can have an open kitchen where you can see what's going on.
Exactly. That's a good analogy, yeah. So what I want is an open kitchen. They have a closed kitchen, okay?
Got it.
But it's not the case that the customers are going to go into the kitchen and start helping with cooking. And that's important. That's very important, as we'll see. So, incidentally, people don't really understand what individuals are. These are some individuals. Drawn a couple of individuals here superimposed on the fractal model in a particular society. And you see what the individuals are persons who have shared different collections of these groups that the entire fractal is made out of. Every individual has a head in the top level groups. Otherwise, they wouldn't be a member of the society, the nation, or whatever it is. But if you look at their arms and legs, they impact on different subgroups. Individuals are collections of subgroups of the fractal. Generally, individuals think they're like that inset on the top left-hand corner. They think they've got all the knowledge in their heads. And we're encouraged to think of that when we're educated at school. If you get what the school teacher is telling you, somehow you're told that that's because you're really clever. But it's actually because you're really good at absorbing what you're getting from the society.
Interesting.
The analogy I like to use is of a thermometer in a beaker. If you imagine a thermometer in a beaker of water, the thermometer is in there saying, hey,
yes,
I'm a 78 degree, but it's not the thermometer that's a 78 degree, it's the water.
Does this mean, in your view, IQ is akin to being more of a porous sponge? Or you don't want to get into that? That's different.
I want to get into it, but I want to get into it by to use it to think about artificial intelligence. In other words, I'll come to this in a bit, but the key to artificial intelligence is not to make a brain, but to make a brain that's capable of absorbing what it can from the social groups in which it's embedded. And those two things are different.
So I would imagine that intelligence involves both the ability to learn quickly, but then to manipulate and produce something new.
Intelligence you can think of it as a orthogonal dimension to what we're talking about. Because if somebody is autistic, for instance, they may not get any of this. They may not be able to embed themselves in social groups if they're high on the Asperger's scale or something of that sort. But they wouldn't be able to get this if they were dead. So all the features of a living body, like having blood circulating and a heart that beats and so on and so forth, is necessary to gain stuff from the group in which you're in. But all these things are an orthogonal dimension to what we're talking about, which is the fact that you get what you know from the group or groups in which you're set.
Okay, yeah? Understood.
So that's the individual, it's very important when you start thinking about economics, which talks about utility functions and so on, because a lot of economics depends on imagining free markets with independent individuals, but individuals aren't independent. One of the reasons I speak English and not Chinese is I was brought up in England, not China. It has nothing to do with my choice. That's the sociology of knowledge. Most of what you know is a function of where and when you were brought up. Anyway, let's go along here. Oh, here we are. Just the very question you were asking. There is a nice model of a brain invented by a man called Curt, who's one of the senior people in artificial intelligence, who sees it as a hierarchically arranged series of pattern recognition. I think that's a pretty good model of a brain. I mean, people who are brain experts say it's too simple and so forth, but it seems to me to capture an awful lot of what a brain is. But the trouble with, this is from a book I wrote on deep learning a few years ago. The trouble with this model of the brain, the obsession with the brain that you find in artificial intelligence, is it doesn't take into account that actually the brain looks like this. It's what I call social. They're called guy on the left, Sam, or the girl on the left, Sam. She might be Samantha. But on the right, this is social Sam, who is actually hierarchical pattern recognizers need another level. And they're all the other brains in society, or those parts of society with which they interact. And all those other brains feed in to social Sam's brain via the senses, mostly the ears. A lot of it's conversation. Okay. It's also going to be written language as well. And that's the difference between artificial intelligence that is mostly conceived nowadays and artificial intelligence that it needs to be. It's got to have that extra layer. But notice from the previous slides, that extra layer has to be restricted. It can't be just everybody, because that's not how you get socialized.
Uh-huh.
You get socialized by going into narrow bounded groups, which all have a consistency and know something and know the same thing. And this starts in babyhood. You're taught language by your carers in babyhood. You're given a consistent world in babyhood. Your carer says, bunny, bunny. Your carer doesn't say bunny. Oh, no, maybe that's a dog. Otherwise, you'd never learn the word bunny.
Mm-hmm.
The carer says, this is red. The carer says, this is red, but philosophers or certain other people would call this blue. Okay?
That's hilarious.
You get this consistency in a very bounded community, which is the family. And then as you grow up, the boundaries spread a bit to the tribe or to the school, and eventually to the university, and eventually to those other groups that we saw in the fractal model. Now, you can probably anticipate what I'm going to say, but large learning models that we hear a lot about these days, like ChatGPT, the difficulty with them is they get their input from anywhere, the whole of the web. And that's why they do what's called hallucinating, because they haven't been brought up in small, bounded groups. And that's a problem that's going to have to be solved. They try and solve it retrospectively by giving it rules to tell it what it can't say. You mustn't be a misogynist. You mustn't explain to people how to make bombs, etc., etc. But this is all an attempt to do retrospective socialization, because it hasn't got its natural socialization from bounded groups. So once we've got that idea, we can see what happens in the case of social media. In the case of social media, the nice little groups, of which A is an example with its bounded perimeter, suddenly starts getting input from all over the place, like those dashed lines that I've put in there. They come from anybody. Anybody can say whether gravitational waves have been discovered or not. Anybody can say why they're not gravitational waves that have been discovered. Anybody can invent some conspiracy theory to show why they're not gravitational waves. All the philosophical assumptions that had to be included in order to get to gravitational waves can be violated by anybody from anywhere. And instead of getting that nice bounded group that you see in A, becomes something that looks like C with its amorphous pattern. And the nice fractal model, which you have in D, becomes something that looks like E, where there are no clear bounded groups at all. This creates a society which is perfectly ready to have power groups emerge from within it just by their use of power, those ugly-looking stars that I've put in panel E. And that's what's happening to our society now, the erosion of truth. Truth is made in a fractal model like D if we want to keep civilization as we know it. This is why I'm saying science is such an important institution. Science is, I think, a unique institution because it's obsessed with truth. It's raison d'etre, or to use more technical sociological language, its founding aspirations are truth-seeking. It wants to find correspondence truth. Correspondence truth is truth about how the world works. And then if you get into one of these groups of the sort I described earlier on, you'll discover that in order to collectively discover correspondence truth, you have to engage in moral truth. Moral truth is the easiest thing. It's the decision, I'm not going to tell a lie. Your mother asks you, did you smash the vase? You're either going to say I did or I didn't. You're a morally truthful person if you tell her the truth. And scientists working in these small groups discover they're not going to get anywhere unless they tell the truth to each other. So science is an institution that is invested with truth. Correspondence truth leads to moral truth. And then because moral truth it's easier than anything else, it's easier than correspondence truth. But it's not actually trivially easy because you have various kinds of biases. And so scientists invent methods to try and eliminate biases, such as double-blind experiments. But what we now know is that none of these methods are foolproof. They're jolly good things to try to do because they help, but they're not foolproof. I mean, let's take what's often described as the gold standard of science, which is a double-blind experiment. Well, supposing you're doing a double-blind experiment on the efficacy of a drug. You give one group a placebo, you give the other group a genuine drug, and you don't tell them which one they're getting, and then you look at the result. But supposing the genuine drug has some side effects, placebo doesn't, everybody's going to know whether they're taking the placebo or the drug. And it's still a good thing to do, but it's not foolproof. And it can't be used everywhere. I mean, one of the nicest jokes I know about double-blind experiments is the advice never to use a parachute because they've never been double-blind tested. And so, but, let's think that all the methods in science are good things, but we should think of them as more like values, more like philosophical decisions to use them rather than absolutely foolproof things. But this is the important point. What I'm claiming here, because I want to be as provocative as possible, is that there are no other institutions like science in terms of the obsession with truth. And one of the things that me and one of my colleagues is going to do, well, the next thing we're going to do is sit down and have a long, long argument about whether the law competes with science as a truth-generating institution. I don't think it does. He, at the moment, he's a professor of law, does think it does, and I'm going to convince him he's wrong. But you can start thinking about all the institutions that there are, and we're going to do this. We're going to start thinking about lots of the institutions in the fractal model to try and work out whether there's anything else that has the obsession with truth in the way that science does. And I don't think it does. Now, you can see why I was so, I won't say disappointed, I won't even say surprised, but fascinated by the fact that the gravitational wave physicists spent 5 months lying to journalists when I am describing them as an institution which is obsessed with truth. And you can see why I thought they'd be better off telling the truth during those 5 months rather than lying to journalists. So this is what I want to happen. I want science to feed truth back into society in the ways that I've suggested, as an object lesson and as a check and balance on potential dictators. What have we got to do to get that to happen? Well, first of all, I think we've got to change science education and concentrate less on training for careers in science. Only a very small number of people who are taught science go on to careers in science. So science education should be more widespread to wider groups of people, but should be taught more in a way that takes away the mythology and uses the kind of idea of the image of science that I'm trying to present here. So teach more science, concentrating on its essential nature. Teach it for all those who need it in their work, e.g. all those in government. Okay, so that's one thing we can do. I've got no idea how this could possibly be done, but I think we should cut competition in science. Get rid of the prizes. I mean, one of the reasons that the gravitational wave physicists wanted to pull their rabbit out of the hat is because they were afraid of being preempted. Well, if it happened, it wouldn't matter to the public. I mean, what did the public get out of the discovery of gravitational waves? It's something edifying. And it wouldn't matter if it happened a bit earlier or a bit later, or it wouldn't matter who did it, really. Who cares about individual scientists among the general public? What you care about is what's been discovered. That's what's edifying, not who discovered it.
Right.
And then, I've already said this, stop the process of turning scientific knowledge into a marketable commodity. We need science's findings, but we need its culture even more to save democratic society. I think we're in a terrifying moment in history at the moment, notably in America. It scares the life out of me, and I think we need more of this. And I think we need to change our education system to teach this kind of thing in schools and universities. That's what I'm arguing for.
Thank you, sir. Wonderful presentation.
Well, thank you.
So I'm curious about elimination of prizes. Even if we were to eliminate all prizes, would there not be some emergent one, such as who has the most citations?
Yeah, I mean, I said I don't know how you're going to get rid of the prizes. I will say this for the gravitational wave community in which I was embedded. I did hear often one of the most senior people in the gravitational wave community who did win a Nobel Prize. He often said, we should get rid of the Nobel Prize. It creates too much damn competition. And he'd been burned, actually, in earlier incidents by people who jumped in and tried to preempt who was going to win the Nobel Prize. And he didn't find it very pleasant. I was very pleased to hear that kind of talk. So, I mean, there would be a subgroup of scientists who would be in favor of getting rid of Nobel Prizes, including the Nobel Prize. But whether it actually come about, I don't know. It's not the most important thing, but it's that kind of thing that creates competition. Would people look at their citation list? Well, I know I'm always staring at my citation list. But I mean, you keep it to yourself. I mean, it's not a public thing. So, yeah, it's nice to be cited. But I don't know how you get it right. I don't know how you do any of this. I know what you'd put into a new kind of science teaching syllabus in schools, but I don't know what you'd do to stop the institutions of universities being tied up with competition. I also know, we should stop marketizing science in the same way. And I know how that could be done by a willing government, but I'm not sure there are any willing governments who want to do it.
So the sociology of science means what? And also, how did you get involved in it? Can you please give myself and the audience some background?
Well, I got into it, I suppose, by accident. When I was at school, that's high school, as Americans think of school, I specialized in science. British educational system is quite specialized at high school level. I specialized in science. Then I turned into a sociologist by a series of strange chances. And then I found myself doing a master's degree in sociology. And I had to do some sort of little practical piece of research at the end of the master's degree, just a small thing. And I thought, well, it'd be fun to go back into science laboratories. And so I wandered around the science lab of the University of Essex, where I was at the time. And I stumbled across these people trying to build a new kind of laser called a transversely excited atmospheric pressure carbon dioxide laser, or T laser for short. And I thought, I know what I'll do. I'll try and see how they learn to make this laser, because I learned from them that it's very hard to make it work. And so my first little master's dissertation project was wandering around all the places in Britain where they had a T laser and finding out whether they could make it work, how they made it work. And this eventually got written up in a paper in 1974, which is still being heavily referred to, much to my gratification, even though it was just the little things stuck on the end of my master's dissertation, because it was all about the tacit knowledge. It had the transfer of tacit knowledge rather than explicit knowledge. And after that, I went on to do a PhD, and I decided, well, I'll continue with this kind of study, but I want some more areas where people are competing, and that one of the scientific domains that I studied was the detection of gravitational waves. To cut a long story short, that eventually wound up in another paper. That was quite a breakthrough paper. I got a job and continued in it ever since.
Well, Professor Harry Collins, thank you so much. Your work is on screen right now and then in the description for people who want to follow up. And we definitely need to follow up with another podcast. So if you're listening to this and you have questions, I'm sure you do, leave them in the comments section below. Thank you, Professor.
Thank you.
Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. There's now a website, curtjaimungal.org, and that has a mailing list. The reason being that large platforms like YouTube, like Patreon, they can disable you for whatever reason, whenever they like. That's just part of the terms of service. Now, a direct mailing list ensures that I have an untrammeled communication with you. Plus, soon I'll be releasing a one-page PDF of my top 10 toes. It's not as Quentin Tarantino as it sounds like. Secondly, if you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for theories of everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in theories of everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/CurtJaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on Toe full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.